We're going to put into practice the variation of parameters formulas that we developed in the previous lesson, the summary of which is on the screen here, but it's also in the previous lesson. The one thing I want to remind you of is when we find W1 and W2, a column in each was replaced by 0 and then f of x. That f of x is the function that we get on the right-hand side of a differential equation after the equation has been put into standard form if necessary. Here the equation we're going to work with is y double prime plus y is equal to the secant of theta times the tangent of theta. Since this is already in standard form, that is the f, in this case, of theta that we're going to be using. First thing we need to do, solve the auxiliary equation to find the complementary function. In this case, m squared plus 1 is equal to 0, which implies that m is equal to plus or minus I, which then means that y sub c is c1 cosine of theta plus c2 sine of theta. I'm going to identify y1 as the cosine of theta and y2 as the sine of theta. My choice of which one is 1 and which one is 2 is completely arbitrary. All that matters is that you keep track of which one was which. The Wronskian of these functions is the 2 by 2 determinant with top row y1 and y2, so cosine of theta and then sine of theta, and the second row is their derivatives, and so negative sine of theta, cosine of theta. Remember to compute the determinant, it is upper left times lower right, and so in this case cosine squared of theta minus, now that's always minus, the product of the lower left times the upper right, that's a negative sine squared of theta, so plus sine squared of theta, and that whole thing is equal to 1. That'll make things pretty easy. This is the first example after all. W1 is the 2 by 2 determinant that we get when we replace the first column using 0 and f of theta, which in this case is the secant of theta times the tangent of theta. The second column is the same as what the Wronskian, sine of theta, cosine of theta. And then we're going to multiply upper left by lower right and get 0. And subtract, so negative, lower left times upper right. Secant of theta, tangent of theta, sine of theta. If you break everything down into sines and cosines and then repackage it, you'll find that that is the tangent squared of theta. Let's move on to W2. The first column of W2 is the same as the first column of W, and so cosine of theta, negative sine of theta. The second column of W2 is the 0 and f of theta from the standard form of the differential equation, and so 0 secant of theta, tangent of theta. And again, the 2 by 2 determinant is computed by multiplying upper left by lower right minus lower left times upper right. The 0 is nice to work with. Cosine times secant is 1. This is going to give us the tangent of theta. U1 is equal to the integral of W1 over W with respect to, in this case, theta. W is 1, and W1 is the negative tangent squared of theta. Now you may remember we don't directly integrate the tangent squared of theta. We use a Pythagorean identity if you need to review it. And negative tangent squared of theta can be replaced by 1 minus the secant squared of theta. We're integrating that with respect to theta. We're going to have theta minus the tangent of theta. You may wonder about the constant of integration. You'll see in a bit why we don't need to write that down. U2 is the integral of W2 over W with respect to theta. Again, W is 1. W2 is the tangent of theta. So we have the integral of the tangent of theta d theta. If I remember correctly, that's the natural log of the absolute value of the secant of theta. Again, we don't need the constant of integration. Again, I'll tell you why in a bit. Yp has the form u1y1 plus u2y2. We said that y1 was the cosine of theta, and that y2 is the sine of theta. So our yp is going to be cosine of theta times theta minus the tangent of theta plus the sine of theta times the natural log of the absolute value of the secant of theta. We can simplify because cosine of theta times tangent of theta is the sine of theta. So y sub p is theta times the cosine of theta minus the sine of theta plus the sine of theta times the natural log of the absolute value of the secant of theta. Further, remember that y is equal to yc plus yp. And so here we have that y is equal to c1 times the cosine of theta plus c2 times the sine of theta from the first step, like 30 minutes ago, plus yp. Well, okay, so I kind of lied to you. Yp in this case is not everything I said it was. Yp has a theta times the cosine of theta and a sine of theta times the natural log of the secant of theta. And you might wonder, what happened to the minus sine of theta? It's represented in c2 times the sine of theta. It's a redundant term. We don't need it. We already have it represented. Furthermore, we'd have exactly the same situation if we had added, say, constants of integration plus c for u1 and say plus d for u2. We'd end up multiplying y1 times c and y2 times d, thereby repeating what we already knew from the complementary function. So this is another one of those glorious processes where we don't need to bother with a constant of integration. And folks, this is the variation of parameters process.